Good morning, Astronomy 1010, and welcome to Lecture 13, Part 2, or what I accidentally called Lecture 14 in the email. This is our final lecture of Astronomy 1010, the solar system. Today, we're going to have a lecture on Jovian interiors and the moons of the four gas giants, or at least some of the moons. We're going to do one final homework set together from Chapter 12, and that's also homework number 12. And then we will end the class. And I will try to finish the grading and compute the grades as soon as possible. I'll probably wait to compute your final grades until after Sunday so that people watching the video later will have a chance to turn in today's homework and Monday's lab. One last final pitch. If you enjoyed this class, if you need another 4-credit lab science class, please take my Astronomy 1020 course in Summer 1, because I really want them to open up a section for Summer 2 so that students who want to take 1020 in Summer 2 will have that opportunity. But, don't take it unless you need it. How did the lab go with the rotation of Jupiter on Monday? Was it smooth? No difficulties? Okay, wonderful. Let's talk about the Jovian planets. You all remember how many planets are visible to the naked eye, right? How many planets can be seen with the naked eye?
Isn't it 5?
That's right. And what are the 5 planets, Ryan?
Venus, Mars, Jupiter.
Don't forget
Saturn and
Mercury.
Mercury. Yeah.
Mercury's tough to see, but it can be seen. The only reason Mercury is hard to see is because it's really close to the sun normally. If you look at the planets with your naked eye, they look like mere stars, except they're brighter, they're larger in angular size, and that makes them brighter. They don't twinkle as much. And that means if people have been observing these planets for thousands of years, they've seen them as points of light on the sky. Galileo, of course, was the first person to resolve Jupiter and Saturn with a telescope. He didn't know about the existence of Neptune or Uranus and Neptune. Even afterwards, if you take pictures of the planets with Earth-based telescopes, you don't get a lot of detail on their surfaces. So the first time humans ever saw the gas giants was probably during the Voyager 1 and 2 missions. And let's look at their orbits for a second. I think I've shown you this slide before, but it's worth mentioning. The Voyager spacecrafts were designed as a grand tour of the outer solar system, and they were both launched in 1977. Voyager 1 made the very first pass-bys of Jupiter and Saturn, and then flung itself out of the solar system into deep space, where it actually continues to travel today and sends back the occasional data point or two to us. Voyager 2 is particularly special because it managed to pass by all 4 of the gas giants. First Jupiter, then Saturn, then Uranus, then Neptune. They referred to it as the Grand Tour. For most humans, for all humans, this was their very first up-close and personal look at the Jovian worlds. They had never seen them before. And the photographs we still use today, and some of the photographs I'm going to show you come from the Voyager spacecrafts. In the years since Voyager did its thing, we have designed 2 more space missions to travel to the gas giants. One of them in the 1990s was the Galileo spacecraft. And the Galileo spacecraft was designed to travel to Jupiter to take high-resolution images of both moons and the planet, and then to drop a probe down into the cloud tops of Jupiter on a sort of kamikaze self-destruct mission so that it could test the atmospheric composition of Jupiter and report back on it. Here's the Galileo spacecraft itself, shown in the clean room at NASA. Always cool to imagine what it would be like to have a job working in some kind of space center like this, right? And somewhere there's a picture of the probe. I can't remember where it is. It was just a very simple mechanism to drop. This is the probe. So it basically had a heat shield, and it drops and descended into the cloud tops of Jupiter to sample the chemical composition. I'm going to show you the results from that mission in just a moment. The other spacecraft that's traveled to the gas giants is the Cassini mission. The Cassini spacecraft is now done because we terminated its mission by dropping it into the cloud tops of Saturn. But Cassini was a sort of, I guess you call the 2000s the naughties, right? A naughty era journey to Saturn, where we took some extremely beautiful high resolution images of its moons, studied the rings, the turbulence in Saturn's atmosphere. There were all kinds of different cool science missions. Weirdly, we have not since traveled to either Uranus or Neptune. So all of the photos that I have to show you from the Uranus and Neptune environment are all from the Voyager spacecraft. I would personally, just based on how crazier the cameras were when we sent the probes to Jupiter and Saturn, sending a modern day camera to Neptune and Uranus would probably show us some very beautiful and creepy pictures and unlock a whole bunch of science. So I'm personally really excited about this next generation of space missions that'll go out there. Okay, so here's my plan for today, and I got a bit of a late start because of technical issues. I want to talk to you about the atmospheres in the interiors of the planets, and then I want to talk to you about their moons, because that's what I think is interesting. So let's take a look at what that Galileo probe discovered when it dropped down into the cloud tops of Jupiter. This is in some ways a study of an atmosphere, and it's a study of our atmosphere which is interesting in comparison to the terrestrial atmospheres that we just talked about. Remember that the gas giants, they don't really have solid surfaces. But like a star, as you descend into the cloud tops, the clouds become thicker, they become warmer and hotter, pressure develops, and probably at some point into the interior, the density gets high that it almost turns into a kind of a gooey liquid. So instead of any particular solid surface, it just starts to turn into slush or mush or pea soup. And eventually the densities become so high that the material is more or less in a solid form. But there's no one solid surface for us to land on. Oops, sorry, 29. Okay, this is what the probe discovered when it dropped down into the atmosphere of Jupiter. Now notice that Jupiter has some designated layers of its atmosphere that are once again based on this graph that we call the temperature scale height diagram. How does temperature change in the atmosphere? Notice that in the absence of a surface, they were still able to define a troposphere by using the tops of the cloud layers. Unlike Earth, which has only water clouds, Jupiter has 3 different cloud systems available to it. At first, at colder temperatures, you get an upper layer of yellow clouds made of ammonia. The ammonia seems to be condensing around negative 210 or negative 220. Sorry, let me try that again. Probably at 190 Kelvin or so. At 190 Kelvin or maybe negative 100 Celsius, that's where we see the ammonia clouds condensing. The red clouds, does anyone remember what the chemical was that the red clouds are made out of? Oh, I guess they tell you. Ammonium hydrosulfide, okay, is another wacky hydrogen ice. And then somewhere around 273 Kelvin, that's where we see water clouds condensing. So think about storms and think about weather systems on Earth. And just think about how much funky weather develops just from having water clouds in our own atmosphere. Now try to imagine how much crazy weather there must be on Jupiter. If you could travel and fly in between these cloud layers, you might see storms of ammonia snowflakes falling down on the tops of the ammonium hydrosulfide clouds. And then these ammonium hydrosulfide clouds might be raining. So there could be rain and sleet and snow made of water and ammonia. There's probably lightning storms. And in fact, we see storm systems in Jupiter in these sort of swirling spots that you see here. So just like on Earth, these storm systems here are hurricanes. And one of the most iconic, of course, is one of the classic features of Jupiter, a massive hurricane, maybe 2 to 3 Earths in diameter. It's called the Great Red Spot. And the Great Red Spot is an unusual storm system in that it's persisted in the cloud tops of Jupiter for as long as we've been observing the planet. Let's think about it. On Earth, when hurricanes develop over the ocean, what eventually causes them to dissipate and break up?
Lack of water, so like going over land.
Going over land. So would it make sense to you, Ian, that perhaps these storm systems don't break apart over longer periods of time? Well, what am I doing here?
Yeah, definitely.
Right, because the idea is if there's no land and you build a big hurricane, it could potentially just keep swirling around for a long time. It is interesting to note that when Voyager first passed the planet Neptune, let's see if I can find a picture of it here. My mouse is acting a little funny. Uranus has almost a featureless green cloud layer to it, and we'll talk about that in a moment. But when Voyager first passed by Neptune, they detected the presence of what was known at the time as the Great Dark Spot, a sort of giant storm system similar to Jupiter's Great Red Spot. We have not been past Neptune since, but we have continued to image it with the Hubble Space Telescope. All subsequent images from the Hubble have shown that this has disappeared and no longer exists in the cloud layers of Neptune. And that suggests that perhaps the Great Red Spot itself might one day disappear. There are other weird aspects to the Great Red Spot. It's not a normal storm system like the ones that you have on Earth. Normally, we associate hurricanes on Earth with low pressure cloud systems. But the Great Red Spot, it seems to sort of have a high pressure storm center associated with this. And you can see this if you image the planet in infrared light. Let's go back to slide 30 here, and let's look at these two pictures at the bottom. On the left, you see an image of Jupiter probably taken with Hubble Space Telescope at visible wavelengths. And over here, we see a similar image of Jupiter, but this is taken with an infrared telescope. Notice that some places on Jupiter are brighter, and other places, other bands are darker. What would make these bright bands bright in the infrared? What are we detecting there?
They're giving off more infrared light.
Which means they are
Hotter.
That's right. Warmer objects will be brighter in the infrared. So let's look over here, Ian. We can see that for the most part, the brighter bands seem to correspond with the red clouds, which are made of what element? Or what molecule?
Was it like ammonia phosphate or something?
Ammonia hydrosulfide, but close enough. Well, close enough for an astronomer, not for a chemist. Okay. Ammonia something or other, okay? Does it make sense that the red clouds would be warmer? What does that mean if they're warmer? Let's think about our temperature scale height diagram. If they're warmer, they must be.
They're higher pressure and higher density.
But they're also deeper into the belly of Jupiter, correct?
Yeah.
See, that's something we don't always think about when we look at a picture of Jupiter's cloud tops. They kind of look like they're all swirling around together, right? But in fact, some of these cloud layers, as we saw from the probe's return data, some of those cloud layers are much deeper at a much lower altitude than others. But we can't really tell that because we're looking from above, right? If the Great Red Spot is red, we would also anticipate that like the other red layers, it would be deeper into the belly of Jupiter. But look what color the great red spot is in the infrared diagram. It's black. So what does that tell us about the great red spot?
It's on its surface.
It's high above the other clouds, or at least closer to the level of the ammonia clouds, right? So it's almost as if the ammonia clouds have sucked up some of that ammonium hydrosulfide, and this hurricane's just been blowing around Jupiter for hundreds of years since we've observed it for the first time. In fact, rather than the great red spot disappearing, what we did discover is that recently a new storm system showed up that scientists have dubbed Great Red Spot Junior. So today, when we imaged the planet Jupiter, we found that a new red spot showed up called Great Red Spot Jupiter. And it could be that this develops over time into a permanent storm system. We'll have to see. So there's something funny going on with the Great Red Spot, and there's a lot of cool atmospheric science to be done there. Let's just take some notes on this, and then we'll look at the cloud layers of the other planets. Oops, got some lighting issues here. So we'll start with the cloud layers of Jupiter. I'd like to do these in color, but I don't think I have. Well, I guess I could use orange for yellow, okay? So we have a layer of ammonium clouds, and they sit above a layer of ammonium hydrosulfide, which then sit below a layer of water clouds. And we can see that each of these has a different condensation point. The temperature here is 273 Kelvin. Let's see if I can do this without screwing up here. It seems to be around maybe 220 Kelvin for the ammonium hydrosulfide. And maybe a temperature around 190 Kelvin for the ammonia clouds. So we can see there are different temperatures at which these different hydrogen ices form. Class, let's do a little remembering. What percentage of Jupiter's composition do these sorts of clouds make up by mass? You learned the composition of the gas giants last class. These are, of course, hydrogen ices. What fraction?
70%.
Hell no.
I was gonna guess 1%, but then I wanted to double check.
But that's correct, isn't it, Jenna?
Oh, the ices. Sorry, I was looking at regular hydrogen.
Right. But these are hydrogen ices, but that's not the same as diatomic hydrogen, right, Kim?
Yep.
For instance, ammonia. Ammonia is a nitrogen with 3 hydrogens stuck to it. The 70% hydrogen that makes up most of Jupiter are just 2 hydrogen atoms stuck together, okay? So if all of this stuff makes up 1%, Jenna, what do you think Jupiter would look like if we could remove the 1% hydrogen ices?
I don't think we would see the striation marks. It would be more monocolor.
I like your striation marks. That's nice. Yeah, it would be monocolor. You wouldn't see any of this cool this is going to be one of the homework questions today, Jenna. You wouldn't see any of this cool stuff, would you? What color do you think it would be? I guess there's no reason you should know what color hydrogen.
Yeah, I was gonna guess like the water cloud color because it's mostly on the surface.
Yeah, it probably, if we look at Neptune, oh, sorry, if we look at Uranus, where's Uranus? It would probably look like Uranus, but just instead of being bluish or greenish, it would be gray or black and white. Hydrogen and helium are colorless gases, so they would probably just look like a gray, black and white photograph or something like that. It would probably be pretty frickin' boring. I think the moral of that story is just like on Earth, it's the minor ingredients that give planets so much of their color and appearance. What you see on a planet is not what you get. You see the little sprinkles, you see the salts and the peppers. You don't see the main entree when you look at the atmosphere. That's true of our own planet if you think about it, because water makes up 0.5% of our atmosphere, yet all you see when you look at the atmosphere of Earth are water clouds. Same kind of thing going on in Jupiter. So suppose we wanted to ask about the atmospheres of the other planets. So let's look at some pictures of them for a second. So slide 3 here shows Jupiter. You can see at least 3 of our different hydrogen ices. Do you guys see those little flecks of blue in there? What do you think those little flecks of blue are being caused by? What hydrogen ice looks blue? Let's find out. Here's a picture of Saturn. Notice you can sort of see some of the stripes that you see in Jupiter, but they appear to be washed out. If you had to pick one color that represented the color of Saturn, what do you think it would be?
Like yellow.
You know, yellowish, huh? Right? Okay, let's look at so Uranus famously has a greenish color, right? And then Neptune has a dark blue color. We haven't dropped probes into their atmospheres, but we can study them. We can study them using spectroscopy. And over here, this is what you discover. All right, what do you see happening? Let's see if you guys can make some sort of sense out of this graphical data. We already looked at Jupiter, and we saw that there were different depths into Jupiter's body at which these different molecules or hydrogen ices condensed into clouds. What do you see happening with the cloud layers on Saturn? What's the difference between the cloud layers in Jupiter and the cloud layer? They're all made of the same thing after all, but their appearances are quite different.
There's less pressure on Saturn, so
Well,
that they condense lower down, I guess.
Yeah, technically this is a graph of temperature, but you could make the same argument with temperature, Ian. You know that it gets warmer as well as higher pressure as we go deeper into the belly of Saturn. So what you can see is the depths at which those cloud layers are forming are deeper into the belly of Saturn. How would you say that relates to the appearance of Saturn that you saw in that previous photograph? So you said pretty much the right thing. So why does Saturn look like this then? And not like Jupiter? Sorry.
I guess because maybe, I mean, it looked like the water was way lower down than everything else, so maybe you're just seeing more of the other ones.
Which ones are you seeing?
I don't remember this. I know they're both ammonia, but ammonia hydrosulfide and
well, you said yourself that if it was any color, it would be kind of yellowish, correct?
Yeah.
What clouds what compound makes up the yellow clouds?
I cannot remember for the life of me.
Can anyone?
Ammonia.
Ammonia.
Oh, it's just ammonia?
Yeah, just ammonia.
Oh, okay.
Ian, you're looking through a big, thick blanket of ammonia haze. Probably. What do you think? How far away is Saturn from the sun? Let's think about this. Jupiter is 5 AU from the sun. And, oops, sorry. So Jupiter is 5 AU from the sun. Saturn is 10 AU from the sun. To get from Jupiter to Saturn, you have to go double the distance, right? What do you think Saturn would look like if we could take the finger of God and push it to 5 AU?
I imagine it might get at least partially sucked up by Jupiter.
No, I'm
Or-
not talking about that. I'm just saying if you moved it to Jupiter's distance, not if you moved it next to Jupiter.
Okay.
I'm talking about the appearance of the cloud layers here, not about cosmic collisions and fun stuff.
Would it look?
Maybe the warmer temperatures would bring certain clouds higher up.
Maybe it would get all fucking stripy like Jupiter is. That's kind of my point, right? My point is Saturn doesn't look different because it's made of different stuff. Saturn looks different because it's farther from the sun and therefore has a colder surface temperature. The reason why you don't see that same types of stripes is because the clouds are forming so much deeper that you're actually looking through a big wall of ammonia haze. Do you know there's some pretty weird cloud patterns that Cassini discovered on Saturn? One of the things that really blew my mind in particular, Cassini Saturn hexagon. They orbited over the pole of Saturn and discovered that the cloud tops made a perfect hexagonal shape. I have no fucking clue what that's about. That's some kind of a cool atmospheric turbulence effect where the turbulence of the atmosphere is making this perfect hexagon. I mean, it looks pretty darn hexagon-y. And that's sort of spooky to me. The first time I saw that, I thought, oh my gosh, it's like there's some kind of alien intelligence inside the body of Saturn trying to communicate to us with geometrical shapes. But of course, that's not what's really going on. What's going on is some kind of cool physics that allows this atmosphere to create turbulent boundaries that form a hexagon. Very cool stuff, you know?
Yeah, it's really cool because it also, like, I mean, I don't know if there's a good example of it, but, you know, seeing different shapes and patterns reforming
In nature, right?
levels.
And especially when you see them repeat themselves from snowflake crystals to planetary atmospheres, there's some kind of geometrical, mathematical harmony in nature that is quite pleasing. Thank you for understanding what I was trying to say there, because I wasn't being very articulate about it.
Yeah, no. I think that's really cool.
Let's go back to slide 42 for a hot second. What do you see happening on Uranus and Neptune that we don't see happening in Jupiter and Saturn?
Methane.
Methane starts to condense. And it looks to me from this graphical data like the temperature with which methane condenses is somewhere around 70 to 80 Kelvin or so, right? So in other words, methane, what color does methane make when it condenses? We had notes on this before.
Blue.
Blue, Kim, very good. So it never quite gets cold enough on Jupiter or Saturn for methane to condense, although it's probably there. In fact, earlier, do you remember I was showing you those little blue flecks in Jupiter's atmosphere? I was hypothesizing that maybe there were some very high altitude methane clouds, but I don't know. Okay, so why do you think Uranus looks green and Neptune looks blue when they're all basically made out of the same stuff?
It's probably also similar thing with Saturn and Jupiter, where one is further away.
Right,
but Jenna, what were you going to say?
Oh, I was going to say the same thing, just the distance, the difference.
Okay, but all right, so tell me where the green comes from then. Do you see it? Do you see why green?
Probably the ammonia, right?
The ammonia is yellow and it mixes with the methane, with this blue.
Yeah.
But there's enough intermixing at those temperatures for methane and ammonia to get a green color. But by the time you get out to Neptune, it's so darn cold that methane clouds just blanket the entire planet. So in other words, Ian, the actual colorful appearance, the four gas giants look totally unique and different, but it's really one factor that's determining why they look different. And what is that factor?
Temperature.
Or in other words, distance from the sun. Do you guys remember how we talked about the three fundamental properties of a planet being mass or size, distance from the sun, and rotation? We can see that those rules apply to Jovians every bit as much as they apply to terrestrial planets. Distance from the sun has a powerful effect on the appearance of the planets. Our probe probably got down to about 300 kilometers below the tops of the ammonia clouds, Notice we defined the 0 kilometers as the top of the ammonia clouds. And after 300 kilometers, the thing just got crushed by pressures and temperatures. What if we could go deeper into Jupiter, all the way to the bottom? What would we find? This is what we believe the interior of Jupiter looks like. And we've got it up against Earth by comparison. And this is just a very lovely slide. Now, at first, the hydrogen and helium gas would be in a gaseous layer. But notice something crazy. After you get down to about 9/10 of the radius, pressures become so high that hydrogen condenses into a bloody liquid. And at some point, maybe about 2/3 of its radius, the pressures become so great that you actually compress hydrogen into a metallic form. Hydrogen is the most volatile gas on the entire periodic table of elements. I can tell you that when I worked in an infrared telescope lab, we sometimes cooled the sensor chips with liquid helium, which was at like 20 or 30 Kelvin, but we never once cooled them with liquid hydrogen. You want to know why? Because humans do not have the technology to compress hydrogen into a liquid. This is and the sun is much too hot for any of this. So probably the only places in the entire universe where you could find hydrogen in the metallic or in the liquid form would be inside the belly of Jupiter or maybe Saturn. Something else that's worth thinking about, hydrogen is kind of a weird version of a metal. There are metals and then there are metals. Let's look at our periodic table of the elements. Sometimes I like to call up that kind of colorful one because it's just non-threatening and it's easy to look at. This is the one that I like. And you guys are familiar with metals being things like iron and cobalt and nickel and copper. Those are transition metals or basic metals. Then you've got these weird things over here, like hydrogen occupies a column called the alkali metals. And alkali metals are pretty weird because they all have a single valence electron dangling off them. And unlike gas giants, which are on the other side of the periodic table, and these guys are hardly reactive at all, the elements that are in this column are super, super, super reactive. That extra electron they have makes them violent, and it makes them do crazy things when they come into contact with other compounds. Do you guys know about sodium, for instance? See, I'm trying to have us imagine, what would metallic hydrogen look like? Since it occupies the same column as sodium and potassium, I'd imagine that it would resemble something like sodium. Sodium, you've probably never gotten to see before. They don't put it in the kids' chemistry sets anymore because you can make too many explosives with it. Okay, I know, because I'm old enough that when I had this in my chemistry set as a kid, they actually gave you a little sample wrapped in plastic. And they had to wrap it in plastic because if you touched it, even the moisture on your fingertips was enough to give you a horrible chemical burn or even set it on fire, okay? So this is probably what metallic hydrogen represents or is similar to. In fact, a fun thing to do, if you can get your hands on a brick of sodium, is to throw sodium into water. And there's a cool YouTube video of some hillbillies throwing, there's all kinds of different ones, but this is the one that I like here. Let's have some show and tell time. Did I share the sound with you guys? Can you hear the sound from this video?
Yeah, I can hear the sound.
Let's indulge ourselves for just 1 minute, okay? And let's just watch what happens when you throw sodium in water.
Vlog it. I'm recording it. And
You're sodium. Who wants to throw it in?
oh, Trevor.
I do.
I will.
Here,
Give me the glove. All right, I'm gonna just keep throwing it.
Oh,
I
explosion!
need a slow motion vid. Hold on.
It's funny because it reminds me of what I was like when I was
We are recording.
Wait,
Wait. You want
me to throw it real far?
Hold on. Wait.
Can I throw it real far or no?
This is so.
All right, here he goes. He's gonna chuck it off the dock here.
I don't really want to stay
The camera will stabilize
That
it.
way?
Yeah.
Oh, jeez.
Okay.
And then it explodes.
Yeah!
Pretty fun stuff, right? So if you think about it, the entire interior of Jupiter is made of a highly reactive metal like that. If only, they always saw, oh, if we had a big enough lake, then Saturn would float. If we had a big enough lake, Jupiter would explode. Okay? I was going to have you take some notes on that, but screw it. You've seen the picture. Let's just instead compare it. Let's get rid of that so I don't get any ads. Let's compare with, oh, by the way, what do you see down here at the core of Jupiter? A core of rock and metal, but not just rock and metal, but also hydrogen ices. Do you guys remember how this relates to the lecture that we had last class or the last two classes? Why is it interesting to me that there's a roughly larger than Earth-sized lump of rock, metal, and ices?
Because they're volatiles.
Not just about the, okay, we talked about this. So why is it significant that there's ice down there in the core of Jupiter?
I still have to do last lecture, but my guess would be, I mean, I don't know if this is relevant at all, but since it that's exactly what terrestrial planets are made out of. So if
Except
it's
not. Wait, Ian, you're drawing the wrong conclusion. I'm talking about the proto-solar nebula and how Jupiter formed.
well, I was going to say that it would have been a terrestrial planet that would have been too big to
But why
sustain.
is, so you're still missing a key component that I was hoping someone could help with. Why is it too big? Kim?
Low melting point?
But not for rock and metal, but for
Ices. It's
Ices.
too far from the sun.
That's right. That's right. Ian, the technical term is Jupiter formed outside the frost line of our solar system. And outside the frost line, the original seed of the planet that we call a planetesimal formed not just from rock and metal like a terrestrial planet, but now you could add hydrogen ices in solid form to the mass. And eventually the mass got high enough where, sorry, oops, this is the wrong slide. Eventually the mass got high enough where you could suck the hydrogen and helium from the protosolar nebula. See? The whole reason that all this top layered stuff there is because the original lump that formed the planet did not just have rock and metal, but it had rock, metal, and plus ice. All right. What if we could compare Jupiter to the other Jovian planets? Well, this is what we believe would be like the interiors of the other planets. Apparently, Saturn at 1/10 the mass is still dense enough for both liquid hydrogen and metallic hydrogen to condense. On the other hand, Uranus and Neptune are about the same mass and about the same size. They are both 1/10 Saturn's mass. Therefore, they are 1/100ths of Jupiter's mass. We believe that this is not quite dense enough to condense hydrogen into a liquid or solid state. On the other hand, we believe that these two gas giants have extra amounts of water, methane, and ammonia, and that inside them is kind of a slushy slurry of icy, liquidy, slushy water, methane, and ammonia. This is one of the reasons why Uranus and Neptune's are sometimes called ice giants. Jupiter and Saturn are called gas giants. On the other hand, do we think that gas giants is actually an appropriate name for these planets?
Probably not, given that it seems like most of their composition is not even gaseous.
Right, most of it is condensed into a solid metallic form. By the way, what are two conditions for a planetary magnetic field?
Volcanoes and
Nope.
the Hadley cells.
No, you're thinking atmospheres. I'm talking magnetic fields are generated in the interiors of planets.
Well, it would have to, I'm probably a little bit off, but like the rotation, right?
That's right. And Jupiter rotates in 10 hours. So rapid rotation. What's the
And
other condition?
Hot interior.
Hot interior. Does Jupiter seem to have the conditions for a planetary magnetic field?
Yeah.
Yeah. All four gas giants have magnetic fields, and Jupiter in particular has the most powerful magnetic field in the entire solar system. It's hard to really explain to you guys how potent Jupiter's magnetosphere is. It actually has effects on the moons, which I'll talk about in just a second. Solar winds interact with the Jovian magnetic field in complex ways. You can actually image the aurora borealis on Jupiter, Saturn, and Uranus, Neptune. The auroras on Jupiter are like 5 times the size of Earth. They're absolutely insane. They're wild storm systems. In fact, here's a picture of aurora borealis happening on Saturn. We have one on Neptune, but we don't have a good image on Uranus. If you think about it, magnetic fields are a funky connection between the planet Earth and the Jovian planets. That's the one thing that we have in common with Jovians, is none of the other terrestrials have a magnetic field, but we do because we're the biggest and the fastest spinning terrestrial. So and look at the magnetic field axis tilts with respect to their spin axis. Saturn's is lined up and Jupiter and Earth are kind of close, but Uranus and Neptune have magnetic dipoles, which are like almost perpendicular to their rotation axes. We know that in the history of our own magnetic field, our geomagnetic field has reversed several times. So it might be that we're catching Neptune and Uranus in a period of time where their magnetic fields are flipping or something. It's kind of interesting to think about. Okay. That's as much time as I want to spend talking about the planets themselves. Let's take some notes about Jovian moons with the short time that we have left. I made a point last class, which is that the moons of Jupiter, Saturn, Uranus, and Neptune are many, and some of them are quite large. Some of them are, in fact, roughly the size of either Mercury or our moon. And you can see that here in this slide, which shows some of the more famous moons of the 4 gas giants in relationship to the size of Mercury, the moon, and Pluto at the bottom. Some of the moons, 3 of them in particular, Ganymede, Callisto, and Titan, are all larger than the planet Mercury. And that means if they were orbiting the sun, they would be bona fide, totally 100% too legit to quit planets. They just happen to orbit Jupiter and Saturn, so we don't call them planets, we call them moons. Now, Ian, what's the dominant form of geology on Mercury?
Rock and metals, right?
That's the composition. I'm asking about the geology.
Okay.
Pick one of the 4 geological forces.
Yeah, I guess cratering. I feel like I should remember this. Yeah.
It's a big cratered ball of rock. How about the moon?
Also cratering.
Right. So what would you expect to be the dominant form of geology on these planets?
Cratering.
It turns out it's not. And does anyone else so it's not Ian's fault. He didn't hear Monday's lecture yet. Do you guys remember why we're going to see more interesting geology on worlds that are every bit as small as Mercury and the moon?
Is it maybe because of being in the orbit of these such high gravity?
That turns out to somewhat be the case, especially for Io. But Ryan's kind of hitting closer to it in his comment here. He said ice jets, but in fact, Ryan, you should have skipped the jets part and just left it at ices. Remember, the fact that we're outside the frost line means many of these worlds are covered in ices, and ices can fracture and crack at different temperatures and pressures, and they can also form cryovolcanoes, and they can form ice tectonics and even atmospheres made of different stuff. So we're actually going to see quite a bit of geology on these worlds, but it's kind of a bizarro ice geology, okay? And that's what's going to be fun. Let me take some notes that I think are important concepts to think about with moons. When I think, so I don't have time to cover all the Jovian moons, but I'll show you some of my favorites, and we'll sort of play planetary scientist and see if we can understand their geology together. I'd like to classify Jovian moons into 3 categories. There's your large moon. A large moon is one whose diameter is, say, greater than 1,000 kilometers. Or I'm tempted, you know what? Let's not say diameter. Let's say radius. A large moon whose radius is greater than 1,000 kilometers first of all, will definitely be spherical in shape. Gravity will deform it into a sphere. Usually, large moons are ones which have several different types of geology, usually, but not always, few craters. We're going to see that's sort of a lie. Sometimes they can even have an atmosphere, or at least those frost jets that Ryan referred to. These are the ones that I'm going to focus on since I can't cover all the moons of each planet. Then we have to pay a lot of attention to what I would call your medium-sized moons. A medium-sized moon is one that's around 500 kilometers in radius or so. Or at least greater than or equal to 500 kilometers. I might have actually wanted to choose diameter here. I've always said diameter. Today I'm saying radius. I'm not sure why. It's a factor of 2. Medium-sized moons are usually spherical. Instead of having several different types of geology, we tend to find one dominant form of geology that is not cratering. One type of, let's call geology that isn't cratering cool geology, okay? That's a little weird to say, but we'll put it that way. It's one type of cool geology, something that you wouldn't expect. They often do, sorry, I've got some glare on my board. Where's the glare coming from? I don't know, but I can't seem to fix it. If I stand there, I do. Okay. They usually have some cratering, meaning their surfaces are a little bit older than the large moons. Some cratering, and I don't know. I don't know what else to say. Then we have a lot of these small moons. Small moons are one whose radius or diameter is less than 500 kilometers, okay? And small moons are usually just beat up, heavily cratered. You could either think of them as asteroids or ice balls. Especially once you get out to Saturn, most of the compositions of these things are just beat up, heavily cratered asteroids or ice balls. They're usually not spherical. They're usually shaped like a potato, okay? Sorry. That says not spherical, but my handwriting gets worse as I get towards the bottom of the board.
So I was going to ask, and I don't know if this is something you may have answered last class, but what really would distinguish, like, why are they small moons and not part of like rings or something like that? Like, are they just asteroids that are just big enough to?
There is a gradient, but if something is a particle that orbits a planet, it's kind of considered a moon. Planets with rings, it's messy, right? For instance, let me show you a picture, Ian, that will help identify the weirdness of the question you just asked. In Saturn's ring system, there are moons that are buried inside the rings. They're hard to detect, but they're called gap moons, and sometimes they're called shepherd moons. In the case of today's homework, we're going to do a homework problem examining Prometheus and Pandora, 2 shepherd moons that help herd the icy particles of the ring system. Prometheus and Pandora themselves are probably made of giant ice balls. So if you asked what made them different than a ring system, I don't know, because we could take an image of them probably. That's just, you know what I mean? It's actually kind of a gradient-like concept.
Yeah, yeah.
let me show you some other examples really quick of an example of a small moon of Saturn. I really hope I have time to go over these. Take a look at Phoebe here. Phoebe is probably like 50 kilometers or so across. It just so happened that Cassini went really, really close to it. Notice that its actual composition is primarily ice, but just look at the violence that this thing has had to undergo during its 4.6 billion year journey around Saturn. I mean, this thing has been smacked up 6 ways to Sunday, probably with some cratering that is so deep and intense. Do you see this large thing? That's an impact that probably went on the verge of busting this thing apart into a bunch of ice shards. And in fact, some of the small moons, in fact, there's one moon of Uranus called Miranda. And the first time I ever, there are some moons that look all kinds of crazy, like famously one of the moons of Saturn, Mimas. There's a resemblance to another famous moon. Okay. All right. So there, look at the size of the impact crater on that thing, though. One of the first times I saw this moon of Uranus called Miranda, by the way, Uranus is the only astronomical body where we deviated from our usual tradition of naming moons after mythological creatures or peoples. All of the Uranian moons are named after Shakespearean characters. So Oberon, Puck, Miranda, things like that. The first time I saw the picture of Miranda, I thought, this kind of looks to me like maybe it's some ice tectonics or something like that. But the whole thing just looked so bizarre, I couldn't wrap my mind around it. And then I read an essay that suggested that probably what happened to this moon is it got struck with some kind of a really massive meteoroid or planetesimal, so violent that it kind of broke the planet apart into fragments, and then gravity kind of awkwardly glued those fragments back together, almost like a broken vase or something like that. So this planet,
it's kind of like, you know, after the moon kind of broke off from Earth, it's kind of the
leftover bits, yes,
reattaching parts of
reattach themselves. Except in our own moon, it was probably warm enough to sort of smooth out the rock, where here it's probably quite cold and it's mostly made of ice instead of rock and metal. So the gravity isn't quite strong enough to warm it and deform it. It just glued together kind of like messed up fragments.
Cool.
Here are the moons that I would like us to consider with the very little time we have left. And I just want to show some pictures and talk about their geology and entertain you with them, okay? And then we'll move on to our homework. For anyone crazy enough to think about taking my final exam, there would probably be quite a few questions about moons. And the moons that we would be expected to study, which now I don't really have to test you on, I just have to entertain you with, are from Jupiter. The largest of the moons are called the 4 Galilean moons, and they are Io, Europa, Ganymede, and Callisto. Those are the 4 really large moons of Jupiter. From Saturn, I definitely like to cover the Saturnian moon Titan, but there are a couple of smaller moons that I think are worth mentioning. One is Enceladus. Enceladus taught us a lot of cool science about moons versus rings. And the one that I love in particular, just because of its cool features, I've already shown this moon to you, but I might show it to you again, Iapetus. Uranus only has a bunch of medium-sized moons, and I just showed you one of them, but I don't think I'm going to come back to them because I just don't have the time to do it. There's one moon of Neptune that I'd like to cover. Neptune has a really large moon called Triton. So with the exception of Enceladus and Iapetus, which are the medium-sized moons, all Triton, Titan, Io, Europa, and Ganymede are the biggest moons in our solar system. Each of them are probably worth talking about. So let's go to Io for a moment, and let's think about something that, so here are our moons here, Io, Europa, Ganymede, and Callisto. Io has the distinguishing feature of being the most geologically active moon in our entire solar system. Feast your eyes on this beautiful photograph here of the surface of Io. Every black pit that you see there, every black dot is a volcano protruding from the surface of this moon. And those rings of yellow that you see are frozen sulfur dioxide frost that's just raining back down onto the surface of this moon.
So this is true color?
True color.
Cool.
Amazing, right? It looks like pizza. Now, Ian, you ironically suggested the reason. Io is approximately exactly the size of our own moon. Our own moon has nothing like this number of volcanoes. Io is so volcanically active that when the Galileo spacecraft flew by it, it actually got real-time images of volcanoes blasting sulfur dioxide gas and frost up into its atmosphere and then raining back down onto the surface. So we actually got images of active volcanism on another planetary body. Ian, you suggested the reason why an object the size of our own moon might be so volcanically active. And what is that?
Sorry, it froze for a second there.
Oh, sure.
I caught the end of your question though. But I was saying that maybe it has something to do with it being in the orbit of such a high gravity planet. So it's
That's
kind
right.
of.
So this is an example of where size is not causing internal heat, but it's actually an artifact called tidal friction. Even planets like Earth and the Moon cause each other to bulge along their equators. They deviate from a perfect sphere into a kind of football shape that we call an oblate spheroid. The oblate spheroid has a major axis, which is the long axis of the football, and that tends to point towards the planet. But think about it. Imagine this thing rotates a little bit. If it spins around Jupiter, suddenly its major axis is going to not point towards Jupiter. And then physics is going to do one of two things to it, and probably both. The first thing it is going to do is it's going to apply a twisting torque and try to rotate the moon back along the direction of Jupiter. The second thing that will eventually change its rotational period. In fact, most moons in our solar system are in a set of what we call synchronous rotation. Their spins and their orbits are locked together because of tidal frictional effects. The other thing that tends to happen is the rock itself will change, whoopee, and deform in the direction of the planet. So what you can see happening is it's as if the gravity of Jupiter is just whooping the planet through tidal friction and squeezing and pumping and squeezing and pumping and squeezing and pumping. And you know what happens when you knead pizza dough? When you're making a pizza, it starts to get warm. And the friction of whooping and warping that moon over and over again has actually kept its interior warm and its lithosphere thin to the point where Jupiter's gravity is blasting all these volcanoes off their surface.
So would Io have a magnetic field, since it's probably rotating faster from the gravity and being kept warm internally?
Io turns out, from what I know, to not have, I don't think it has a strong magnetic field, but the next moon, Europa, does for an even more crazy reason. So hold on for a second. Okay, Io's orbit is 42 hours, which is longer than Earth's by 2, right? I bet its spin has become synchronized. So let's see if that's the case. No one's ever asked me that question, and I don't perfectly know the answer. I suspect that Io does not have a magnetic field, but I don't have a good reason why. It's just my hunch. Also, I've never read about it, and I feel like I would have heard about that. That's the only reason why. So let's look at its rotation period. So it's 42 hours for its orbital period, and its rotational period. You see how it says synchronous? That means it's tidally locked. The orbit and the spin are locked together like our own moon. I don't think 42 hours is fast enough to have a potent magnetic field. I think 24 hours is. So that's why, do they have anything about its magnetic field? Control F, mag. Nope, not there. Control F. Excluded the presence of a magnetic field. So I was correct. That would have been an interesting enough observation that I feel like I would have heard about that. That's why I didn't suspect it, okay? Here's something else that's kind of interesting, and this relates to our homework today. Not only is the spin of Io locked to its orbital revolution, but the orbit of Io is actually tidally locked to the other 4 planets into a set of what is called orbital resonance. Now, this is not a coinky-dink. There's a reason for this. Io completes exactly 4 orbits for every 2 orbits of Europa for every 1 orbit of Ganymede. There's an orbital resonance of 4 to 2 to 1 for their orbits. Now, how could gravity have caused that over 5 billion years? Let's imagine we started off and Io was over here. There is continuously a force of gravity between all of these moons and the planet. And if you calculated all the forces of gravity, these would be the distances between all the different planets, correct? Now let's imagine that we went to some other configuration where the planets were not in an alignment. Here's Io, here's Europa, and let's say here's Ganymede at some later time. Now look at the distances between the planets and the moon. The distance between the planets and the moon don't really change, but notice that the distances between the moons are considerably greater. In which configuration will the gravity be stronger? When the moons are in alignment or when they're at random positions?
Alignment.
Yeah, that minimizes the distance. So what do you think that would do if you have a little gravity enhancement every time the planets line up? It'll kind of slow down their orbit. It'll become a resonance. You know, like when you push a little kid on a swing, you don't just push them at any old random time. You give them a push, a little nudge. They swing and come back, right? And right when it's time for them to descend again, you give them another little nudge. And if you give nudges at the right frequency, you start to create a resonance pattern where the swing amplifies. A similar effect is happening here, and it's called orbital resonance. If the nudges increase every time the planets are aligned, it will temporarily slow them down, and over billions of years of nudges, lock all of their orbits together. You will discover in today's homework, and you'll discover if you poke around yourself, that almost all the moons in the outer solar system are all locked together in funky orbital resonances. In fact, a fun game is just to take any 2 moons from any 2 Jovian planet, to divide their periods, and then see if you can figure out what fraction it is. Sometimes the fractions are obvious, like they'll come out wicked close to 0.5 or 0.75, but sometimes the fractions are weird ones, like 2/7 or 5/8 or something. So you really have to know your fractions well to play that game. One last question about Io. If it's the most volcanically active world in our solar system, what do we normally associate volcanism with in the terrestrial zone?
A thin lithosphere?
Yes, and this has that, but something else. I'm thinking something from last week's lecture.
Is it plate tectonics? Or
That requires water.
hot core?
What do volcanoes produce? That's
Water.
Water. Yeah.
They do produce water. Okay.
Carbon dioxide?
You're missing the point.
Okay.
Atmospheres. Volcanisms create, yes, they create lava, Ryan, but also atmospheres. Don't forget about that. One question you might ask me is, does Io have an atmosphere? No, it does not. Then why? There are 2 reasons. The first is it's really cold on Io because you're 5 times farther from the sun than Earth. So when those volcanoes go off, a lot of the gas particles freeze into condensate and deposit onto the surface. And you can see that in the wild looking pizza colors. There's another thing that's going on too. Jupiter's magnetosphere is actually tearing gas particles off the surface. Now, most gas particles that come from volcanoes are electrically neutral, but not all of them. For instance, there's this crazy Iceland volcano that went off a few years ago. I can't pronounce its name because its name is this. Okay, its name is blah, whatever that is. Okay, but I saw a picture of this. There's a couple of people on Wikipedia who teach you how to pronounce Eyjafjallajökull, whatever it is. Okay, anyways, I can't do that. I'm not Swedish enough, but I want to show you a famous picture of this volcano that I saw in the New York Times that kind of blew my mind. It was a picture of it at night. I'm looking for this here. This is it. These two pictures. This one in particular. It was a picture of gas being forced through this glacier and the most batshit nuts lightning storms I had ever seen in my life. And I had never thought to equate volcanism with lightning storms before, and yet it actually kind of makes sense. Why do clouds build up light charges and create lightning in our own atmosphere? Do you guys know how that works? How does lightning get formed? No. The way lightning is formed is clouds, condensed water droplets, are pushing at high speeds through the atmosphere of Earth, and the friction knocks charges and transfers charge from some molecules to the other ones. Eventually, the clouds lose a bunch of electrons, become positively charged, and the charge imbalance rips a current of electrons right out of the ground. Of course, volcanism will be associated with charged particles because you're pushing gas at high speeds against other gas. Well, now let's imagine that you have a giant electromagnet called Jupiter rotating around you at 10 hours, period. That magnetic field will scoop up plasma particles and then push the neutral gas right off the surface. And in fact, there is an entire donut of charged particles orbiting at Io's radius that we call the Io torus. There is a continuous current of 1 million amps flowing between Io and Jupiter. That's pretty wild. You could power a science research station with that. Dan, I'm sort of running out of time here. Let me just show you a couple of pictures of the other ones, and then we'll stop. The other moon that I really wanted to show you so badly was the next moon of Jupiter. This is the moon Europa. And you'll notice that Europa is a totally different and bizarre world. Everything that you see here is a sheet of frozen water ice. The red colors come from this chemical compound called tholins. Don't ask me about tholins. We recently have made some higher resolution images of Europa. And they're so high resolution and so beautiful that I'd like to share them with you. Let's see if I have them here. So this is a true color photograph of what it looks like. There's Europa in relationship to the size of our moon and Earth. It's about the size of our own moon. And there's, yeah, this is the picture right here. Look at that. Look how beautiful that is. So let's talk about this. Is this a young planetary surface or an old planetary surface? What have we learned?
I would say old. There's a lot of scarring.
Other opinions?
My guess was young, actually.
Jenna's correct. This is a super young planetary surface. How did you know that, Jenna?
I don't see a lot of impact craters.
There's no impact craters. And that means this thing has refreshed itself, at least in the last 100 million years. Completely refreshed itself, Ian. Craters are how we measure age, not other types of features.
Yeah.
Craters and only craters. Jenna had the right instinct. No craters, young surface. Okay, so then what are we looking at? What type of geology is this?
at risk of being very wrong. I remember talking about striation, right, on Mercury from like volcanism. So is it something to do with
Mercury
that?
wasn't volcanism.
Or
It wasn't volcanism.
okay, yeah. See,
Is it plate tectonics?
It's some type of tectonic features. Yeah. These are cracks, massive cracks that developed in the ice sheet that surrounds Europa. And it led us to suspect that underneath the ice, it might be that temperatures become warmer and warm enough for some of that ice to melt into a liquid. Ian mentioned magnetic fields. Europa is the only moon that we know that shows the presence of an induced magnetic field. So when we flew the Voyager missions past Europa, we of course measured it and studied to see whether it had a magnetic field. Measuring a magnetic field is a way of probing the interior of the planet. What they discovered on Europa was something called an induced magnetic field. It had an on-off period of about 10 hours. Why is that significant? 10 hours.
that's the same as Jupiter's, so maybe it's being synced up.
That's right. So what's happening is Jupiter's magnetic field is zipping past Europa every 10 hours. Now, we all know that we're not supposed to drop radios and hair dryers into our bathtubs because we will become electrocuted. But did you know that pure water is actually a perfect insulator that conducts almost no current whatsoever? It's not so much the water that conducts electricity. It's if you dip a pinky finger or a big toe into the bathtub, enough salts will come off your toe to conduct a healthy current of 30 amps, which is plenty enough to kill you. It's not the water, it's the salt that conducts electricity. Now, in a similar fashion, ice, frozen ice, is not a very good conductor of electricity. And that's because the water and whatever salts are in there are frozen solid. So if we see an induced magnetic field, what does that suggest about the moon Europa?
That it's has a lot of internal heat.
Not internal heat, but the idea is that if there was a salty water ocean underneath the ice cracks, there would be a lot of positive and negative ions in terms of salts floating around. And every time Jupiter's magnetic field hit the salty particles, they would spin around in a circle, and they would themselves induce a weak magnetic field, which turned on and off with the period of the moon. In other words, Ian, the induced magnetic field is considered evidence for a massive sub-ice liquid water ocean. A liquid water ocean that's been sitting around and festering and percolating for 4.6 billion years.
So tropical life.
That's right. So I don't know if they have any good pictures. Let's see if they, I have a picture in my slideshow. Oops. But it occurred to me that the model of on Wikipedia, oops, sorry. They might actually have a better picture of this here. If not, then they're doing it wrong. Let's see if I can. Wow, I'm sucking today with the internet, guys. Yeah, this is what I wanted. Oh, by the way, let's look up close. We have super high resolution images. You guys can see that there is a history of cratering on the planet, but how do the craters look different than on other worlds?
They're they're outies. They don't go in.
Yeah, and they're all warped and whoopied. they're outies. I like that. There's so much warping and whooping on these impact craters that we've morphed and disturbed the surface. Like, you can see that there's a lot of really recent ice tectonics covering the surface. Do they have yeah. So they believe that probably what's happening, and I'd like to zoom in on the lower portion of this rather than the upper portion of this, there's probably some internal heating due to tidal friction with Jupiter that creates something like our own mid-Atlantic ridge, a sort of cracked underwater volcanism system that can heat up and liquefy the water. And this location here on Earth, the mid-Atlantic ridge, is where we find a lot of geothermal life disconnected from the solar food chain. There are weird crabs and giant tube worms that live along the mid-ocean ridge vents. If life could develop on Earth near these hydrothermal vents, as they are called, if Europa were to have these hydrothermal vents, there could be a whole ecosystem of organisms that are percolating around underneath this ice that we have yet to discover. And certainly at some point in the future, people will plan a space mission to drill through the ice and put a little probe down there and see what's crawling around. This is probably the most likely place we would find life in our solar system off of Earth. On the other hand, something that you need to appreciate about the ice is the typical thickness of the ice is about 10 kilometers thick. So how deep do our best oil drills go?
I don't remember the number, but it's less than that, right?
Right. And the only thing that's gotten close to that deep would be the what do you call it? The Cola super deep borehole that we lectured about in an earlier lecture. We actually do have the technology to do this, but it would be a hell of a mission to bring a drill of that scope out to Europa and drill through. But man, would the science discovery potential be worth it? I'm probably going to have to end my lecture soon, so I won't get to cover all the moons, and I'm kind of sad about that. But if you guys want a little idea of what it would be like to take the first manned mission to Europa, once again, I'll tip you off to a pretty cool sci-fi movie that I loved called The Europa Report. Actually, one of our fellow Rhode Islanders wrote the script for it. And it is such a cool sci-fi movie because not only is it scary, but it actually has really good science. When I watched this movie, I was amazed at how everything that happened seemed completely plausible and realistic. I would describe Europa Report as kind of like the Blair Witch meets 2001: A Space Odyssey. You're following the first so-called manned mission to Europa, but the whole movie is told from point of view cameras that are stationed on the ship to give it this cinema veritas, or whatever you call it, this reality cinema thing.
Found
And
footage.
one of the things I liked about the movie is the first part of it was just fucking boring, like real space travel would be. They're just going out of their brains for 2 or 3 years, just waiting to get out to Europa, cutting each other's hair and playing dominoes and losing their minds. There's a couple of hijinks that happen. I won't tell you all of them. But man, when they finally get to Europa and land on the surface, it's just fucking terrifying. There's all this particle radiation coming down from Jupiter, so they can't be out on the surface too long, but they're dying to go out to the surface because they've been waiting all this time, and their ship is kind of stuck in a little ice crack. And oh my gosh, let me just say, put the kids to bed, bust out the anchovy pizza, and get ready for a good time. Okay, I actually found this movie to be quite scary. It was pretty enjoyable. So it was just cool to think about some of the things that we've learned about in our space science class just being visualized on the screen. You get like a very visceral picture of it. It's kind of cool. I wanted to tell you about more of the moons, but I've totally busted my budget. And I do believe we should have one last round of torture, one last homework problem, since most of you are weaseling out of the final exam. I think that would be a nice way to end our class together, and I've made it a mandatory assignment, so you have no choice. Okay, so here's what we're going to do. We're going to take a little tea break, and I'm going to find out how to activate my SRIs, my student ratings of instruction, during this tea break. And then I will do the homework with you. You guys can evaluate me, and unless someone's out there is planning on taking the final exam, that will be it. Does that sound cool? All right. It is currently on my iPhone 1:47. So at 2 o'clock, we'll start the final homework. Okay? All right. See you then, guys. All right, everyone. Welcome to our final homework number 12. Hi, Austin. I made an unpleasant, a scary discovery during tea break. I missed the deadline to activate and allow students to do SRIs. Now, I'd have no idea why the deadline would be a week before class ends. Apparently, I didn't read the 10 million emails that came at me fast enough and I missed it. So I'm sorry. I don't know what I can do about that.
Makes you feel better. Some of my other teachers did that too.
Oh, really? Oh, thank God. All right. So I'm in good company or bad company, depending on how you look at it. It's really important for me, for you to hear what you guys thought of the class in an unvarnished way. I enjoy reading those every year. So I was happy to let you guys do it. In my defense, I typically still use the old-fashioned paper ones in school. And I just, because then I've got everyone in the room and I can say, okay, fill them out. So I'm kind of used to just giving them on the last day of class. And that's why I didn't think that the digital ones would have a shelf life to them. Okay, so I apologize. All right, let's call up those questions, everyone. Our final homework, one last homework to go. We can do it. So our name, Astronomy 1010 with your section number. This is homework number 12. Chapter 11, what's our problem?
It's
47,
Sorry,
52, 54,
wait,
and 57.
Sorry, can you start again, Kim?
Yep. 47,
Yep,
52,
yep,
54,
yep.
and 57.
4 problems?
Yeah.
55 is there too.
Oh, sorry. Yeah.
Okay,
I went fast. That's fine.
that's it. All right. So, Kim, why don't you read us number 47?
Okay. Hang on one second. I got to switch over. "47. Minor ingredients matter. Suppose the Jovian planets' atmospheres were composed only of hydrogen and helium, with no hydrogen compounds at all. How would the atmospheres be different in terms of clouds, color, and weather? Explain."
I think I already gave you a hint at how this question works, right? Clouds, how would they be different?
Would look a lot more uniform, kind of smooth, right?
Would there be clouds?
Yes,
What would,
technically.
what would the clouds be made out of?
Hydrogen and helium.
To hydrogen and helium. What is a cloud?
That's a good question.
Do you know what a cloud is, Ian?
Just like a
Are clouds
condensed
on Earth, are
group of-
clouds made of air? What is
No.
air?
No.
Clouds are
it's-
not
it's
made of air.
gas. It's
What are clouds made out of?
condensed gas.
Clouds are not gas.
No, they're ammonia, hydrosulfide, and methane.
On the gas giants, yes. On Earth, clouds are made of water.
Yep.
Yeah.
Would there be clouds on Jupiter if it was only made of hydrogen or helium gas?
No.
I guess
No.
what you're saying is that since there's nothing else, hydrogen and helium are air, so it wouldn't really count.
What I'm saying is, yeah, kind of.
Okay.
But let's say it better than you just said it, Ian, because what you said still bothered me. Clouds are made of condensed water droplets on Earth, right? They're not so much gas, they're liquid or solid ice particles, right? Hydrogen and helium are in the gaseous form. Ergo, they do not form clouds because they do not condense in the troposphere of Jupiter. Do you see what I mean, Ian?
So they're more a liquid than they're more of a less dense liquid than a
Well,
condensed
don't
gas.
think about the deeper down parts. Hydrogen and helium are at the upper layers of Jupiter are strictly a gas. And as they're a gas that does not condense, they do not form clouds.
Yeah.
The only thing that forms clouds are ices. Does that make sense? So in other words, no ices, no clouds. Color?
Well, I said that a second ago, but they'd be
Right.
pretty uniform, not much to look at.
But what would the color be?
I think we said since they're kind of transparent, it'd be like a gray, black.
Yeah, just like a gray. How about weather? Great red
Um,
spots, lightning, storm systems.
Probably a lot less active since there's a lot less moving around.
The only thing that causes weather, if you think about it, are clouds and moisture, right?
Yeah,
You can't have weather when it's just clear air.
yeah,
So all weather is formed by cloud systems on some level, right?
Mhm.
So no clouds, no weather. There wouldn't be anything. It would just be a gray featureless ball. Let's write that down. If Jupiter's atmosphere was 100% hydrogen and helium gas with no hydrogen ices, it would be a very boring planet to look at. There would be no clouds of condensed ammonium or water, and therefore there would be no storms or weather of any kind. Let's also mention the color as well. There would also be no cool, can I use the word stripy? Is stripy a word? All right. Peanut Gallery
Sounds
back there says stripy is a word. There
sounds
would-
scientific.
Yeah, there would be no cool stripe. Oh, actually, I know it's a word. Yeah, I was just looking for that. Wherever it is. I know it's a word because one of my favorite books on my bookshelf is Stripy Animals. Okay. Okay. There would also be no cool stripy cloud layers. I'm going to have to go up so that my back up here at the top. There would be no stripy cloud layers. But only a gray featureless gas ball. I think that pretty much covers our bases there. We addressed the clouds, we addressed the weather, and we addressed the storms. Okay, Ian, let me know when you're done.
I'm good.
All right, I'm erasing. Kim? All right, I'm erasing. Uh, 52. Let's have Ian read 52.
Sounds good. One sec. All right. 52 is Disappearing Moon. Io loses about a ton, and then it says 1,000 kilograms in parentheses of sulfur dioxide per second to Jupiter's magnetosphere. A, at this rate, what fraction of its mass would Io lose in 4.5 billion years? And B, suppose sulfur dioxide currently makes up 1% of Eo's mass. When will Io...
4.5 or 4.6? Would they have us choose there?
4.5, sorry.
All right, that's all right. Is that A? What percent? Let's just do that.
Yes. Okay, sure. And then go back to B, sure.
So let's see how your problem-solving skills have developed since the beginning of this course. I'm willing to bet that at the beginning of this course, if I asked you a question like this, y'all would shit a brick and not do anything, okay? But I bet now at least someone out there knows how to deal with this. How do I solve this problem? We need to find the percentage of Eo's mass loss. First of all, we're going to have to know the mass of Io for this. And since I had it up on my Wikipedia a second ago, let's see if we can get that back. Come on. Oops. Come on. Come on. Where's the Io? Here's the Io. I think its mass is like the moon's. Yeah, 9 times 10 to the 22 kilograms. So we know that the mass of Io is 9 times 10 to the 22 kilograms. What we need to do is figure out if Io's pumping out volcanoes that are being ripped off the planet. Remember that on Io, you have like volcanoes, and when they go off, Jupiter's magnetic field comes by and just magnetic field comes by and rips the gas particles right off. This is telling us that the mass loss rate is 1,000 kilograms per second being pumped out into the Jovian atmosphere. How do I solve this problem? What do I do? I wanted to see if any of you have evolved into problem-solving creatures, people who can think critically about a little math problem and solve it using dimensional analysis, for instance.
Do we find out how many seconds are in a year?
Okay, let's do that. And how do I do that, Jenna?
We'll set up the dimensional analysis.
All right.
So you draw 2 division bars.
Uh-huh.
And then we'll put, okay. And then we'll put 4.5 times 10 to the 9th years on the bottom.
Oh, wait. You want to find out? You
Yeah.
garden path me. Do you want to find out the seconds in 1 year, or do you want to find out the seconds in 4.5 billion years? I don't know what you're trying to do here.
In 1 year.
All right, so then.
Okay. Okay. So we write 1 on the bottom of the first, and then 365 on top. We'll write 1 on the bottom in 24, and then 1. We'll have to do the math for that.
Oh, really? Then we should, if you have to do the math, then we'll just do it.
Isn't it 3,600?
Yeah.
Perfect.
I was hoping, Jenna, that you would know 60 times 60 is 3,600, but whatever. Somebody did.
Thanks, Ian.
Okay,
No
so
problem.
how many seconds are in a year then?
All right. Let's.
I already have it memorized, so.
Is it 10 to the 6th?
False. Count better.
Okay.
Y'all slow. I think
10 to
Jupiter's
the
gonna run out
7th.
of Eo's gonna run out of sulfur dioxide before you guys finish this calculation here.
10 to the 7th.
3.5 times 10 to the 7 seconds. Remember that astronomers remember the number of seconds in a year as pi times 10 to the 7. Okay, so we did that, Jenna, but we're still not solved the problem yet. We want to know the percentage of Eo's mass lost in 4.5 billion years. So what do we do next?
We find out the percentage lost in 1 year.
Okay, sure. So fine. So tell me what to do. That works. That totally works.
We write 1,000 kilograms over a second.
Yep.
Okay, and then we write in the 3.15. No, wait, I'm getting confused. We write,
You're getting confused because you're trying to do numbers and not units. Do units.
yeah. So would seconds go on the bottom or years go on the top?
Well, then you'll have kilogram years per second squared. That doesn't seem to be very helpful.
Okay, so we switch it.
All right.
Seconds on top.
Now seconds will cancel out and you'll do kilograms per year, which is, I think, what you wanted to get, right?
Yes.
You want to know the kilograms lost in 1 year. Okay, so now give me the numbers.
Okay. So on top we put, yep, that one.
You should be able to do that in your head, right, Jenna?
Yep.
What do you got?
It's 315. Oh wait, sorry, 3.15 times 10 to the 10th
That's right. And what are my units?
kilograms per year.
And now what do I do?
All right, and now we multiply it by 4.5 times 10 to the 9th years.
Good. So Jenna, you were able to correctly use your problem solving skills and your dimensional analysis skills to solve this problem without my help. And I'm proud of you for it. Remember, the trick was to continue to use units to guide your thinking, not numbers. That's the big takeaway from my class. What do you get?
One 1.4 times 10 to the 20th.
I'm sorry, say that one more time, buddy. 1.4.
1 times 10. 1.4 times 10 to the 20th.
Nice. And your units?
Kilograms.
Nice. Now let's do that as a percentage of Eo's mass. 1.4 times 10 to the 20 divided by 9 times 10 to the 22. What percentage? Come on.
It looks like it could be 0.0015. So what? 0.15%.
Right. So if it's 0.0015, that's the same as 0.15%, right? I think is how you say that, Ian.
Yeah.
1500?
Yes.
So
Bless you.
thanks.
was a big one.
It was. Not a pretty big fraction of it. Despite pumping out volcanoes every day, it's not losing a ton of matter. I need to erase this so I can tackle part B. Jenna, let me know when you're done. All right. Something that I find weird about myself is I'm more of an observational astronomer than I am a theoretical one. Yet I like doing problem sets more than I like doing labs. What does that say about me? I don't know.
It is pretty confusing.
Yeah. Oh, sorry, we're still doing 52. So what's 52B?
B says 52. Suppose sulfur dioxide currently makes up 1% of EO's mass. When will EO run out of this gas at the current loss rate?
We want to find when EO runs out of SO2. Let's start by taking 1% times the mass of EO. That, you guys should be able to do that in your heads, right? What's the answer to that? Are you serious? I'm going to go change all your grades to F right now if you can't do this in your head.
Would it be 9 times 10 to the 20th kilograms?
Thank you. Thank you. That's a 100th, right? So you divide by 100. And that's just of sulfur dioxide. So we know what the rate is. The rate is 1,000 kilograms per second. So let's use our dimensional analysis skills. What units will our final answer have?
Seconds.
Okay, so how do I get that?
Put that on the top and kilograms on the bottom.
Kilograms per second divided by kilograms gives you what units?
Seconds.
False.
Seconds per kilogram?
No, kilograms
Oh,
cancel,
give
leaving you with 1/seconds.
Yeah.
1/seconds is not the same as seconds, Jenna. That seconds is on the bottom of the top, which essentially means the bottom, right?
Yeah. Yeah.
So try again. That's not going to work. Try something different.
Would you put the first seconds on the top and then put 1,000 kilograms on the top?
What do you mean by the first seconds? What's the first seconds?
So just flip the kilograms per second upside down.
Oh, you mean put it on the bottom?
Put seconds on the top and kilograms on the bottom.
Fine. Let's look at it your way then. Now what do I do?
What Jenna was saying, but flip the other way. So seconds on the bottom and kilograms on top.
Wait, hold on. You just made me put the seconds on the top and the kilograms on the bottom. Now you're telling me to put the kilograms on top and the seconds on the bottom. That don't make no damn sense. Which way do you want it? I thought you guys had problem solving skills. Y'all can't think your way out of a paper bag here. Come on.
Well, I guess I'm thinking we put 1 second times and then we put the fraction, like, or you know what I mean? Like you put seconds.
Look, you've got two numbers to work with. You have this number and you have this number. Arrange them in such a way, multiplication and division, that only seconds remain. Can you do that? It's like For
Yep,
me, it's like a jigsaw puzzle that has two pieces and you all can't figure out the way to plug them together, okay? Come on, I'm just teasing you. You can do this. You can do this.
What?
I'm trying to anger you to do it right.
Sorry, my brain is like empty right now.
I got it. I think I got it. I think I
All
got
right,
it.
what do you do?
Okay. Well, I can't see the board. Hold on. You put 9 times 10 to the 20th kilograms,
Yep.
and then you multiply by the division bar. We put kilograms on the bottom and seconds on top, and we put 1,000 to 1.
Right. So I believe by the associative law of multiplication, it doesn't really matter which direction I multiply them, right? The important thing is this goes on the top, kilograms per second goes. Can I tell you what I wanted to hear? Because maybe that'll help you understand. I wanted you all to go, oh, if I put kilograms on the top and kilograms per second on the bottom, then kilograms will cancel out and 1/1 seconds is seconds. That's all I wanted you to do. But that job was a little too big for you. You did kind of get there. You did it in your own way. You inverted the kilograms per second. And then after a few failed attempts, you realized that you need to multiply it by a reservoir of kilograms. Whatever. I'm just trying to get you to think about solving problems in a different way. What's the answer then?
9 times 10 to the 17th.
Okay. Now let's convert that to years using the conversion factor that you guys developed earlier. What's the conversion factor?
1 year to 3.15 times 10 to the 7th seconds.
Nice. So how many years will it take EO to run out of SO2?
You could round it. You could round it to about 3 times 10 to the 10th.
Or maybe 30 billion years. So I guess EO is never going to run out of sulfur dioxide, is it? Will we have to worry about this in 30 billion years? Are we going to be around in 30 billion years?
Most likely not.
Why not?
I mean, if you mean specifically us right now, definitely not. But if you mean the human race, the sun is probably going to blow up before then, right?
That's my point. My point is you got to take astronomy 1020 so that you can learn that the sun only has 5 billion years left to live. Boom, boom, plug for astronomy 1020.
I'm taking it. I signed up.
Yes, yes, yes. Thank you, Ian. That's great.
In all honesty, the human race will probably die before the sun even goes.
Yeah, that's right, Ryan.
Oh, definitely.
We'll be
At the
lucky.
rate we're going, we're going to take ourselves out of this world.
That's probably painfully true, my friend. But you know, either we do it or the asteroids do it. Which way do you want it to be, you know? All right. Anyways, is there a part C? No.
Forgot that was me. No, there is not a part C.
Cool. Let's move on to 54. Ryan, you down to read 54 for us?
Yep.
All right. I'm going to erase this stuff, guys. What are you making? That smells funny. Oh, okay. Sounds not very meaty. Chapter 11, 54. Okay.
Prometheus and Pandora.
Oh,
These two moons
remember
orbit
those?
Saturn.
Sorry, Ryan. Remember those
Oh.
crazy shepherd moons that I showed you guys in today's lecture? This problem's about them and they're kind of nutty. Hey, Ryan, before you start reading, let's draw a picture together, okay? So this is Prometheus and Pandora. This is about why moons that look like they're close to each other aren't actually close to each other at all. So let's draw a picture of Saturn. And somewhere in the ring system are 2 moons. And I can't remember which one is farther away. Look at the numbers really quick, Ryan. Which one's farther from Saturn? Is it Prometheus?
Pandora appears to be farther.
Really? So why does that not sound right to me? You could be right. You have the numbers, so you should be right.
I'm just basing it off of how it's ordered because Prometheus is first, then Pandora, and the numbers are.
But they give you the distances and the problem.
Yeah, but the way
Yes, it's 139,000.
I'm
And
Ryan, I am sorry, I doubted you. Okay, so Pandora is here, and Prometheus is there, right? Everyone see what's going on? And this is the F ring. Okay, now that we've drawn this picture, sorry, Ryan, could you read us the problem?
Yep. Prometheus and Pandora. These 2 moons orbit Saturn at 139,350 and 141,700 kilometers, respectively.
Okay, can I get those numbers one more time?
Yep. The first one for Prometheus is 139,350 kilometers, while Pandora is 141,700 kilometers.
Okay.
Using Newton's version of Kepler's third law, find their 2 orbital periods. Find the percent difference in their distance from Saturn and in orbital periods.
Okay. In other words, these guys are racing around Saturn together in circular orbits. In a way, it kind of looks like they're close to each other because this one is here and this one's a little further out. You're about to learn that just because things are close in orbital radius does not mean they spend a lot of time together. For starters, let's convert their periods. This is kind of a big problem, so I'm going to speed things up because you guys can be a little slow. Let's convert both of these to meters by multiplying by 1,000 meters to kilometers on both sides. And that's going to give me 141.7 times 10 to the 6 meters. This is going to give me, 139.35 times 10 to the 6 meters, okay? And now let's do some Newton's version of Kepler's third law. Let's start with Pandora. For Pandora, we have period equals the square root of 2 times big G, 7 times 10 to the negative 11 meters cubed per kilogram per second squared times the distance, a cubed, 141.7 million meters cubed. Wait a minute. I totally am screwing this up. I started to do escape velocity. It's 4 times pi squared times a cubed. I apologize, guys. Divided by big G times the mass of Saturn. I think the mass of Saturn is 5 times 10 to the 26 kilograms. 5.7 times 10 to the 26 kilograms. We'll use 2 sig figs. Can you guys do that for me, please? $70 out. Nice.
I got roughly 53,000. And
What'd you get?
I said I got roughly 53,000.
How many hours is that?
That's what I'm going to figure out.
Three sig figs. 14.7 hours. Right? Yeah? Whatever. What should we do next? What should we do next?
We do the same thing for pro.
Okay, so you guys are going to have to write it again, but I don't have to. I can cheat. I can do pro, and I can change this to 139.35. Give me the seconds and give me the hours. Coffee over there?
Listen, it's too soon.
No, some tea. Make me some Earl Grey. All right. Okay, I just want some. Okay. What'd you get? Oh, Phil's looking out the window. Hey, Phil, come here. Did you guys get to see this guy last time? This is Phil. Phil's
I
a
love
temporary
him
guest
so
at my
much.
house. And he likes looking out the window and hiding in the closet and scratching my little blankets. Okay.
Perfect timing because my cat just got here.
Oh, really?
Yeah.
I think I pissed off Phil when I chased after him. I'm sorry, Phil. Oh, he's running to hide. He's mad at me now. Oh, cool. What's your cat's name, Ian?
His name is Zeus.
Zeus.
Oh, he sat down with me.
Aw. I think Phil's going to be a little angry with me for a while.
Yeah.
Hey, can I get a number, guys? Oh,
Where's the cat?
oh, you missed the cat? I
Ah,
know you, Jenny, but he's kind of mad at me. He's hiding under the table right now because he was peeking out the window and I grabbed him and he tried to run on me.
Jenny, join your class, Professor. She's so excited.
Oh, that's wonderful. Which one did you sign up for?
for the
I think it was
Solar?
whatever semester 2 or session 2 is.
Cool. Well, we're psyched to have you, and it's going to be a good time. I'm sure you're going to show up to class every day, just like Austin did.
yeah.
She's the freaking reason I don't show up, Professor.
All right. Guys, what'd you get for a number? Because I want to
I got about 52,000 if you round it
How
seconds.
many hours would that be?
I still have to do that. I just finished punching it out.
Divide by 3,600.
Yeah. Uh, 14.4.
Let's not do the percentages. Let's just note that the orbital distances are close. Also, the orbital periods are also close. They're 2 to 3% off from each other, okay? And yet, even though they look close, I've got something to tell you that's not easily predictable. Pandora and Prometheus do not spend a lot of time near each other. Can you understand why?
Probably because their orbital periods are similar. So if they didn't start at the same point, they're going to kind of.
Even if they do start at the same point, one will begin to drift away from the other, correct?
Yeah.
All right, part B is where it's going to get confusing. So who is reading this problem? Ryan? Ryan, when you're done, I'm going to erase and you're going to read me. That was all part A, by the way.
All right.
I'm erasing, everyone. I'm erasing.
I just have to say something real quick. Michael Collins from Apollo died today. And it's so weird because we're actually talking about the moons. I just got the thing.
Ken, I meant to tell you that because I when I took my tea break, I drank some coffee and I opened up the New York Times or something and it said, yeah, Michael Collins, the third man on the moon. He's the one who stayed up in the spacecraft while Neil Armstrong and Buzz Aldrin went down to the surface. He died today. So kind of an important milestone in space science history. Kim, thank you for sharing that because I meant to mention that to the class. Go read his obituary. Okay, go ahead and read part B, Ryan.
Consider the two in a race around Saturn. In one Prometheus orbit, how far behind is Pandora in units of time? And how many Prometheus orbits will Pandora have fallen behind by one of its own orbital periods? Convert this number of periods back into units of time. This is how often the satellite passes by each other.
Okay, this is a little bit confusing, so I want you to imagine something. Let's imagine. Oh, that didn't sound good. What did you do? That's my beautiful top. Love, did you break it? Okay. We can glue it, I think. Sorry, there was just a catastrophe in the kitchen. All right, guys, let's imagine Prometheus goes around once, and I think its orbit was 14.4 hours, correct? Could someone confirm that?
Professor,
Yes,
Yes.
that's correct.
I just had something come to me.
Yep.
I'm thinking that there's a 0.3 hour difference between these two orbits.
Exactly.
So I don't know what the heck was read to me. That sounded like a different language, but in order to calculate the amount of whatever, we're going to have to see who's behind. And we know that one of their orbits is 0.3 hours. So we're going to have to see, like, okay, how long will it take? How many orbits will it take to make up that 0.3 hour
Hold
difference?
on, let's be smart about this, Austin. The
Yes.
0.3 hour offset happens every completion of which moon?
Of both of them,
No, only of one of them,
of Prometheus.
Prometheus. So the first Prometheus orbit, you lag by 0.3. The second
Yes.
Prometheus orbit, 0.6. The third, we want to know how long does it take to cycle back around. So let's calculate the number of Prometheus orbits until you drift behind by one Pandora period, right?
Which would be 14.7 hours.
But how do we find the
would it
number?
be
How do we find the
53,000?
number of Prometheus orbits? Yes, it's 14.7 hours, and then what do we do?
Divide by 0.3.
Yes, we divide that by 0.3 hours, and that's weirdly that's the number of Prometheus orbits, even though we divided by the Pandora orbit. So how many? What is that number?
49.
So that's 49 Pro orbits. I'm glad that you got into that, Austin, because the first time I did this problem, I had to like stop and think about it, and it was a cool exercise in my mind. It's 49 Pro
Not all
orbits
naturally talented.
for Pan to drift back by one orbit. Okay, what did it say to do next then, Ryan? Oh, it said then convert this back into time. So how do we convert this back into time? By multiplying by Prometheus or by Pandora's orbits?
Since it's Promethean orbits, we would do Prometheus, right?
That's right. Now we're going to multiply 49 times 14.4 hours. And what's that give us?
49 times 14.4.
Yeah, whatever that is.
Professor,
Yeah, sorry.
I'm sorry to interrupt you guys' role, but I do have to go somewhere, so I'm just gonna watch the rest of this lecture on like some other time. I'm sorry.
That's okay.
So-
Wait, we're so close to the end. Can we just finish this and then you
We're
only
right there, Nori.
Okay,
Nori, let's at least finish the third problem if you can do that. Can you do that?
probably not. I'm not. I've been kind of lost a little bit.
Really?
A little bit,
You
yeah.
were a little drifty during the lecture. I couldn't tell if you were pissed off or tired or what was going on.
No, I've been going through a lot, but it's okay.
Well, you're still here with us, so I'm proud of you for that. And
Thanks.
we're with you, okay? We're with you as your classmates and friends. This is
Thanks.
706 hours. And I
Yeah.
think that's all we had to do for this, right, Ryan? That's how often they line up. Best friends, okay. Now you can at least say, Nori, that you're done with 3 problems. So later on, you can just nab 55 and 56. That's my point, okay? I don't know what the timestamp is in this video right now, but whatever, you'll figure it out.
It's
For
it's
sure.
been almost.
I'll find it.
All right.
I'll just look at one I left.
I'll post this as soon as I can, Nori. Please don't forget to do those last 2 problems. It's the last thing.
Yeah.
to do. And
No
thank you
sweat.
for being a part of our class. And I hope to see you again someday. And I hope that things are going okay.
Thank you.
All
Have
right.
a good one, you guys.
Bye, everyone. Bye, Nori. I mean,
Bye.
okay, so 706 hours, even though they're only 0.3 hours off, they only line up. How many days is that?
706 divided by 24.
Every month. They're only close to each other once a month. Isn't that weird?
I was feeling it, Professor.
You were feeling, I could tell you had those feels. I liked it.
Kind of
Spirit of Saturn.
The spirit of Saturn, that's right.
I tricked everyone in the chat. I said this problem sucks, and then everyone was like, "Yeah, it sucks, it sucks." And I was like, "Psych, I know exactly what to do."
So the first time I did this problem, I also thought, Austin,
I meant it though. That wasn't.
one thing I think about when I do these problems is, did I take away some learning message? The first time I did this problem, I thought it sucked. And then I realized, oh, wow, I learned something about moons, which is moons that look like they're next to each other do not actually spend a lot of time next to each other. The moons that do spend time next to each other are ones that have orbital resonances, whole integer ratios. And that's what Jenna is going to read to us next. So assuming that we finish this problem, let's move on to 55, and Jenna's going to read that.
Okay. Orbital resonances. Using the data in Appendix E, identify the orbital resonance relationship between Titan and Hyperion. Hint, if the orbital period of one were 1.5, the orbital period of the other, we would say that they were in a 3:2 resonance. Which medium-sized moon is in a...
Let's do part B next, Jenna. Sorry to cut you off. Jenna,
That's
to
okay.
do this kind of problem, we need some really precise data. We could do it from the book, but let's just grab the moons from Wikipedia. I think they should have a bunch of their moons nearby. Moons, 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 moons. Where's the damn moons of Saturn? Natural satellites. Okay, we want Titan. And we want, the other one was Hyperion, correct?
Yes.
Oh, wow. So by the way, look at these two here. Oh, shoot. I was hoping to show them by distance. No dice. Titan and Hyperion are further out there. Here's Hyperion. Okay. Hyperion has an orbital period of 21.276 days. So let's write that down, 21.276 days. Titan shoot. Huh. Oh, thank you. Thank you. Jasmine green tea will be just great. Thank you. Here's Titan. 15.945 days. Now, the first time you look at these, do these numbers look like they have anything to do with each other at all? Nope. Let's try dividing the period of Titan by the period of Hyperion. And let's look at what happens on our calculators. 15.945 divided by 21.276. Is that a random number?
Not really. It comes out to just about 0.75.
With like spooky kind of precision, right, Ian? At 0.749, it's suspiciously close to what whole integer fraction?
3/4.
That's right. So what does that mean then?
There's, I mean, I don't know if this is the correct way to phrase it, but there's a 3/4 resonance between the two.
That's not the right, that's not the traditional way we do it. Let me start with a different way. In how many orbits of Titan will Hyperion produce how many orbits? They're equal to each other in some weird way.
Like 3/4 of Titan, or a
No,
whole...
no. Let's do it in whole orbits.
Yep. So a whole Titan orbit is 3/4 of Hyperion's orbit.
Titan's orbit is 3/4, but now let's think logically through this.
Yeah.
In how many orbits of Titan will how many orbits of Hyperion be completed?
In 3 orbits of Titan, 4 orbits of Hyperion.
You screwed it up.
Or the other way around?
It's the other way around because
Okay.
weirdly it's upside down, Ian. In 4 orbits of Titan, there will be completed exactly three orbits of Hyperion. Do you see how that's reversed? That's a trick to this.
Yeah.
So we say, this is how we write it. There exists a 4 to 3 orbital resonance between Titan and Hyperion. You have to word that properly. It's easy to screw up. There exists a 4 to 3 orbital resonance between Titan and Hyperion. Titan makes 4 orbits for every 3 of Hyperion's, okay? That was all part A, by the way. Easy, easy problem, but big concept. All right, Ian, let's try B. Oh, I'm sorry, Jenna was reading.
Yep.
Jenna, I'm gonna erase this, everyone. Go ahead, Jenna.
Okay. Sorry, I lost my spot. Oh, which medium-sized moon is in a 2-to-1 resonance with Enceladus?
Enceladus. Actually, they screwed this up. If it's a 2-to-1 orbital resonance with Enceladus, what they really meant is Enceladus does 2 orbits to every 1 orbit of that moon. So we're looking for longer periods, okay? We're looking for a medium-sized moon there. So let's go. So what is the period of Enceladus? By the way, one of the things I'm sad about in today's lecture is because of my wackadoos this morning, being late plus technical difficulties. I ran out of moon time, which I will forever be sad about. But Enceladus is like a really beautiful moon of Titan. The first time I saw it, I saw a black and white image and I really didn't get it. It wasn't until I saw a true color image that I understood why. Sometimes it does like a slideshow view. Why is it doing that now? Enceladus, like Europa, has some beautiful ice sheets with like frost jets that shoot off the surface. But some of the high color images from it, I was hoping they'd have one. It's so sad that they wouldn't have one of them here. They refer to the shapes on its surface as tiger stripes. Very, very beautiful. Do you guys see all that? That's water. That's all frozen water, but look, some of the water has formed ice tectonic sheets. And when we flew by, we actually watched geysers, jets of water shooting out into the Saturnian system. Why was that a holy cow moment for us? Because one of the issues that another problem brings up is icy ring particles in Saturn actually collide with each other all the time. And that means over billions of years, you'd expect them to grind themselves up into bits and to disappear. Jupiter's rings are almost gone, so are Neptune's and Uranus's. The trick to why Saturn has such prominent rings is Saturn has medium-sized moons which shoot water jets out into the space environment, and those water jets replenish the ring systems. And this explains, these jets are related to why Saturn has a big, beautiful ring system today. It's kind of a very cool planetary science problem. Anyways, I tried to squeeze that in there. I cheated, okay? Let's look at the orbital period. 1.370 days. So what are we going to do to figure out which moon is in orbital resonance 2-1?
I assume it's the moon with double the
Yes.
Yeah. Hyperion.
So, oh wait, 1.370 days.
Would it be
times 4.
half? Because it's. Oh no. Yeah, you're right. I mixed it up.
It's a little goofy, yeah. So Enceladus to this moon is 2-1. There's an ambiguity there that's confusing. The first time I did it, Ian, I searched for a planet with half the period, and I didn't find one. I got screwed up too. So we're looking for 2.74 days. It turns out that there's a couple of moons in orbital resonance, but only one is a medium-sized moon. Periods of moons of Saturn. I should just tell you the answer. I was hoping you'd have to look at a table to do it, as was the book. Oh, wow, they have all this. I think it's Dione. 2.74. You see that? That takes care of 55. One last problem and then our class is done. Woo! Austin, I guess you're the only one who hasn't read. If you'd like to take us home.
I'll do it. Just give me 1 second, please.
Sure. Huh? When? Oh, now. Oh, great.
All right, let's do it. All right, problem 57. Titan's
Hold on,
evolving
hold on.
atmosphere.
Sorry, Austin, give me a sec.
Oh my.
I know, I'm not ready for you. All right, but I'm ready for you now. What's the title?
All right. Titan's evolving atmosphere.
Actually, Austin, I've got to do something. Oh, you went dark for a second. While Austin's going dark, let me show you guys something. One of the things that makes Titan, moon of Saturn, so cool, okay, is Titan is the only moon in our solar system to have an atmosphere besides the terrestrial giants, okay? Another cool thing about Titan's atmosphere is that it's made 90% of diatomic nitrogen. Why do I think that's cute?
Because most of Earth's atmosphere is also nitrogen.
So it's kind of similar to ours, except it's wicked freaking cold on Titan because Titan is 10 AU from the sun. Believe it or not, we actually landed a probe on the surface of Titan during the Cassini mission. And what we expected to find, because we had done imaging through the clouds at longer wavelengths, we could actually see what appeared to be massive lakes and oceans made of condensed methane, CH4, but also, here was the weird thing, condensed ethane. And ethane is kind of like a gasoline. It's 2 carbons with 4 hydrogens on it. Now, methane is obviously in the clouds of these planets, so that was reasonable. But ethane, how the crapola did ethane end up in lakes? By the way, the probe that landed at its surface it lost one of its antennas. Oh, can you see those dark splotches? Those are all oceans and lakes of ethane. And I'm not much of a chemist. Ethane. So ethane is 2 carbons and 6 hydrogens. It's basically like the kind of propane that you have in your gas grill or something. What do people use it for? If you add an oxygen to it, you can make ethanol, or if you add in a hydroxyl group. So that's basically rivers of booze. Sounds like a planet I want to get lost on. All right, anyways. Let me wait. I have one last thing while we're waiting for Austin to come back. I want to show you a picture from the surface. One of the antennas got bunked on the way down.
I'm back.
Okay, it's okay, Austin. Sorry, we knew you had some troubles there. I want to.
I thought Ian or Jenna was going to be reading the problem. I would have been hurt.
Well, I just kind of took this as an opportunity to yap at people. You know how I like to be. Oh, this is the picture. This is the one picture that we have from the surface of Titan. These little pebbles that you see in the foreground are frozen methane boulders. Okay, that's like a methane snowball. I think they call them blueberries as a joke, but I don't know why. But definitely on the trip down, we used a fisheye lens, and we basically found and saw mountains and rivers. It turns out that my slideshow is actually better than the Wikipedia page. Go figure that. So here's kind of an artist illustration of what you're looking at. If you could go to the surface of Titan, you'd see mountains of frozen water ice and an entire river and waterway system that's actually eerily like Earth's, where there are liquid ethane lakes and ethane rainstorms. And there's even plate tectonics, because here's the descent of the module onto the surface of the moon. And you can see as you descend 30 kilometers, 5 kilometers, those look to me like mountains. But what other geology do I see? Or doesn't that kind of look like yardangs or wind erosion? You've got wind erosion on the surface of Titan. You've got mountains of hard frozen water. You've got lakes of condensed ethane and methane. This is like a bizarro inverted Earth world where it's all this frozen chemistry and frozen geology. And we've only explored a small part of its surface. Who knows what else? There could even be some kind of nitrogen-based life forms on this thing. Who knows, right? This problem explores how those liquid lakes got to Titan. All right, Austin, let her rip.
All right, Professor. Real quick, my father would like to say hi.
Yes. Hello, Austin's dad.
Say thank you. I know.
I hope you.
I like your style.
Thank you very much. That's great. You know, dads, they love the astronomy stuff, so you might as well give them a little.
He loves your shit. He just looks great in the background. All right, Titan's evolving atmosphere.
Yep.
Titan's exosphere lies nearly 1,400 kilometers above its surface. What is the escape velocity from this altitude? What is the thermal speed of a hydrogen atom at the exospheric temperature of about 200 Kelvin? Use these answers and the method of mathematical insight 10.2 to comment on whether thermal escape of hydrogen is likely to be important for Titan.
This is another one of those legendary thermal escape problems that is so important to modern day atmospheric science. I would have made you do at least a couple of these had you taken the exam. So it's not bad to squeeze one more out. The radius of Titan is 2,600 kilometers, and the mass is 1.3 times 10 to the 23 kilograms. Because we're going to use an escape velocity formula, we're going to need to convert both of these to meters. And sorry, at 1,000 meters per kilometer, we get 2.6 million meters and 1.4 million meters. Let's draw the picture. Here is Titan. we're about 1,400 kilometers up. And what we're going to do is we're going to imagine that there's a molecule of methane, CH4, which recently had one of the hydrogens bust off of it due to ultraviolet photon radiation. So in comes a UV photon from the sun. It smacks one of our hydrogens off of the methane, and we're going to see if it's possible to escape. The escape velocity is radical 2gm over the radius of Titan plus the height of its orbit. That's r plus h. That's the square root of 2. Let's just put in big G is 7 times 10 to the minus 11. I'm going to actually skip the units. Times the mass, 1.3 times 10 to the 26 kilograms. And if you add this together, you get 4 times 10 to the 6 meters. Why don't you guys punch that up for me? I skipped the units of G because I was feeling very lazy and because I was running out of board space.
I got about 67,000.
I don't know why, but it doesn't sound right to me.
It's
That's
possible.
6 kilometers per second, which would make its escape velocity greater than Earth's. But Titan is smaller than Earth, right?
Yeah.
That can't be right.
All right. Maybe I put something in wrong.
Oh, I think it's because I did 26 kilograms, right? That's my mistake. It's 10 to the 23 kilograms. That wasn't your fault, Ian. That was my fault.
Okay.
I was thinking of the mass of Saturn. Could you punch that one more time for me? Sorry, everyone. Notice, Ian, that I evaluated the answer. The answer didn't make sense. So then I looked for the troubles.
I got about 2,100, 2,100.
Units?
It's a velocity, so meters per second.
Good. How many kilometers per second is that?
2.1.
2.1 kilometers per second. And that's the answer to part A. Now, did we lose Austin again? Austin, are you here? Jenna, I might have you take over if I can't find Austin, okay? So
Okay,
I'm gonna, can I erase this, everyone? I'm not trying to go too quick for you, but all right. All right, so let's try B now.
Okay, so it's asking what is the thermal speed of a hydrogen atom at the exothermic temperature of about 200 Kelvin?
Okay, a hydrogen atom, sorry, has a mass of 1.7 times 10 to the negative 27 kilograms. It's either 1.6 or 1.7. I always get it confused. The thermal speed is radical 2 times K times T divided by the mass of hydrogen. The Boltzmann constant is 1.4 times 10 to the negative 23rd joules per Kelvin times 200 Kelvin, all divided by 1.7 times 10 to the negative 27 kilograms. Why don't you punch that up for me?
I got about 1,800.
Units?
Would that be? Oh God.
Is it still meters per second?
It's
Yeah.
a velocity in MKS.
I was gonna say that, but then I was looking at it and I was like, "Am I thinking about this right?" Yeah, whatever.
It's because you don't know the units of joules off the top of your head. Joules are kilogram meter squared per second squared. Kilograms cancel, kelvins cancel. The square root of meters squared per second squared is meters per second.
Yeah, 100% that.
What's part C say? Let's let Jenna read it because Austin probably you glitched out on this again, right, Austin?
I had to get Jennifer sunscreen from the car.
Oh, okay. Well, why don't we give you a chance to copy this while Jenna reads out part C for us?
All right. So the last is it? Wait, do you want me to read it now?
Go ahead and read it now while Austin's copying.
Okay. Use it. So it says use these answers to comment on whether thermal escape of hydrogen is likely to be important for Titan.
In other words, can you guys piece together a story of how Titan became the planet it did based on these two answers?
Well, we were talking about ethane, right, and how it's weird that it's there. So I would imagine because the hydrogen is escaping, and
Yes.
there's less attached to the methane, it
Yes.
becomes methane, and that's why it's present.
Beautiful, Ian. So, but first of all, let's just test to see if hydrogen can escape. Because Ian, you are exactly right. That's where we're going with this. And it's a beautiful, beautiful story that's neat and tidy, and you can put a bow on it. Austin, I'm going to erase this now. One of the things that we're supposed to do every time is we're supposed to apply the test for atmospheric escape. So the test for ATM loss is V thermal greater than or equal to 1/5 of the escape velocity? Our V thermal is 1.7 kilometers per second, which is obviously much greater than 1/5 of, what was it, 2.1 kilometers per second? If you take 2.1 and you divide it by 5, you get 0.42 kilometers per second. So hydrogen can easily escape. What about your leftover CH4 ion? I don't know what a CH3 thing is, like an ion molecule. It's not a real molecule because it's not electrically neutral. This would be a type of free radical. Do you suspect that a molecule 12, 13, 14, 15 times as heavy would be able to escape? If you multiply 0.42 times 15 square root thereof, you get 1.6 kilometers per second. So the CH3s probably have to stick around, right? They're probably too heavy to escape. Now, just as Ian said, if this happens once, and then if this happens twice from 2 UV photons, Your two CH3 radicals will glue together, and guess what they form? They form ethane. Do you think ethane can escape from Titan's atmosphere? Hell no. In fact, Jenna, I bet that ethane is so heavy that it's likely to do what once it's in the atmosphere of Titan? Now you've got this big ass ethane molecule, which is big and dumb and heavy. What's it gonna do?
Probably fall back to the surface, right?
It's gonna rain back down onto the surface and create those giant lakes of ethane. In other words, Ian, ethane wasn't an important part of the protosolar nebula, but today ethane exists on Titan because of UV photons and thermal escape, right? The chemistry of planets changes over time from things like sunlight and thermal escape. Thermal escape can totally change. And what we see is the surface of the planet is actually undergoing erosion from this. So thermal escape and what happens in the atmosphere can affect the geology of the planet, which is very interesting and cool. Plus, it gave me an excuse to talk about Titan, moon of Saturn. Instead of writing a big passage, let's just write 4 words. This makes ethane lakes. And since it's the last problem, I'll call that a good enough description. Cool beans. Yay, cheers. Well, Astronomy 1010, congratulations on making it through an entire semester with me. I had a very nice time with y'all. You were great. Thanks for participating in live sessions. Turn in the homeworks in the labs and everything's going to be cool. I'll try to calculate the grades on Sunday. Yes, I am in a band, although I haven't had many shows to play during COVID because nobody has any shows to play, but I'm looking forward to the day where I can get back up and play my synthesizer and be a 43-year-old ding dong again. All right.
Professor, maybe we should show everybody some clips from your band. I mean, they're intense.
I'm sure they can find them on their own if they feel like stalking me. I try not to proselytize the band too much during class because it muddies the message, you know, but I do love music as much as I love astronomy. So if you guys can find me out there in IRL or on the internet, I'm happy to chat with you about that stuff.
Look at you, my hair is so...
I'm sorry about the SRIs. I may send you an email if they write back to me and say, no, you totally missed the deadline, but you also totally have to do your SRIs. Well, then I'm in a bit of a catch-22. So if they open them back up and tell me I've got to do this, then I will be sending out an email saying, please, could you advise or evaluate me? On the other hand, I think I'm getting promoted to full professor this summer. So that's a small but important milestone. And that means
tenure or is that full time?
I already have the tenure, but that's basically the highest level. That's the last hoop that I ever have to jump through. And so
Awesome.
after that,
you're gonna easily pay your rent and have some change now.
Well, easily pay my rent is questionable. My rent goes up a lot faster than my salary does. So no, I'm gonna have to move into a smaller place. But anyways, we'll see how this works. My point is, I don't know if I absolutely need the SRIs, but I actually don't, whether I need them or not, I like to hear your unvarnished opinions, like this class is great, this class sucks, whatever. And I like to hear what you guys are thinking. So if I get a chance to do that, I'm going to send out an email. I don't know how that's going to work. Jenny, we'll see you in summer session, right?
Yes.
And I'll see you, Ian, at 1020 summer session. It's nice to have a couple of veterans of the field come back to be good role models for the other students.
Well, I'll tell you what, I really love this class, and I'm much more of a conceptual person than I am like nitty-gritty math stuff. So I appreciate the way you've done it, where you're able to
honestly, when I was a student, I was more of a conceptual, artsy, Englishy kind of person than I ever was a math person. But I forced myself to go into a technical subject because I thought it would be good for my soul and it would round me out. And I think that's true. You can be one of those types of people, Ian, and still learn to do a bit of math, and it can actually keep you from being bamboozled and tricked by charlatans and other snake oil salesmen of the soul, astrologers. Anyways, so,
Professor, we were trying to sign up, and our advisor, well, Jenny's advisor was like, okay, so you want to take astrology with Brendan? And I was like, how could
that advisor should be taking astrology with Brendan, okay? Or not astrology with Brendan. Anyways,
I
you
would
know
love
better
to sign
than
up
that,
for the
Jen.
next class, but CCRI won't let me sign up for classes for some reason.
What? Why not?
You have a hold because you didn't turn in your immunization, Ryan. Email the nurse.
Oh.
Okay.
I guarantee you that's what it is.
Yeah, that was for me at one point. I had a hold because the music.
Okay, Ryan, even if my classes are full, which there should not be, you are a veteran of my course. Hello, sir. Since you're a veteran of my course, I will always try to make a seat for you, just like I did for Austin this semester, okay? So
And I fucked up the bag halfway through, but then I recovered the rock, and we still
you
won the
recovered.
game.
You got back in your groove, okay? So Ryan,
Alex is going to take your class too.
oh, really? That's awesome. I hope you're ready for some big time fun. We're gonna,
I'll help him out. Yeah, he'll be good.
yeah, keep this guy in line, okay? Listen to Jenna because she knows what's up. She was a good student. So make sure he shows up to class, right, Jenna? Jenna, if he doesn't show up, I'm coming for you. All right.
Jenna, are you doing a class next semester?
I do not think I am. I have to check out my requirements. If I need it, I definitely will. But
If you need it, by the way, it satisfies lab science transfers to all universities. So it's easy to get that from my class if you need it. All right.
Yeah, I'm doing 2 lab sciences for the first part of summer. I'm doing organismal bio in this class. Or
all right. That ought to, well, you know, my class will be easy enough to do because I make it streamlined.
Yeah.
So listen, guys, enjoy that sunny 70-degree day and enjoy the rest of your semester. I had a great time and I can't wait to see some of you again. If not, the observatory will be open in the fall. So if you're on campus, come on by and take a look through the telescope. Bring your friends, brothers, kids, boyfriends, whatever. It's a wonderful experience to look at the moon, especially knowing what you know. I would love to show that to you. So I'll see you guys around on campus.
Can I bring
fall.
Nachito?
Yes, you can bring Nachito. As long as he doesn't bite people, that's fine. Okay, but we definitely want to we want to see Nachito Pepito. Doesn't look like he'd bite too much out of me anyway, so that's okay.
Yeah,
No,
well,
bring that little guy. I'm sure he'll be a huge hit. Okay. All right, guys.
Professor, we love you.
Yep. Thank you so much.
Bye.
And I'll see you guys.
Thanks, bye.
Thank you for
later
an
on.
amazing semester.
Take care.